All right. Okay. So this entire second half, what we're going to do is we're going to do this kind of mental exercise called retrosynthetic analysis. We're going to take what we know about our reactions, our reagents, and our direction to give us the desired product we want. Okay. So let's look at this one right here. Okay. So let's see, we have a ketone on here, we have an alkyl group, and we have an amine. Okay. So let's just talk about how to make an amine on there. So to get to aniline, we learned that we had to first nitrate it, and then we can reduce it down with some kind of metal like zinc and acid. Okay. Okay, we can make a methyl group on there by doing a Friedel-Crafts alkylation just on benzene. So that's a possible thing to do there. And we learned we could make ketones from a Friedel-Crafts acylation. Okay, all right. So first thing we have to think about is, okay, which directing groups are ortho and para to see which direction we might want to go. Let's say we have to start all of these reactions with benzene. Okay, so that means we have to put all three groups on. Okay, so what if we put the nitro group on first? Then we would only have an ortho para direction. No, we would only have meta direction for that, right? So let's think about that. If we put the carbonyl group on here, by a Friedel-Crafts reaction, we have to use aluminum chloride. And remember that we can't add aluminum chloride and an amine together at the same time because it'll create a complex and won't react. So we have to think about that. So we have to have the Friedel-Crafts reaction happen before we have a free amine. Okay, so that's important. And we know if we have a Friedel-Crafts product, it's going to be meta-directing, so we can't put this on after this group here. So from all of this, I'm thinking we need to put that methyl group on first. Okay, so I'm going to start with that strategy of putting that methyl group on first. And so let's see, how would we do that? We would do that with, starting with benzene, we would take iodomethane, or any, and aluminum chloride, and that's going to react. And because we're starting with benzene, we're going to put that on, and we're going to stop it at the CH3 right there. Okay. Now, is this the major product? Probably not, because remember, once we get that first alkyl group on there, it can alkylate again. And so we might have some impurity of a xylene or one of those dimethylbenzene compounds. But let's say we can purify it and we can get that on there. So the next thing we want to do is we want to use that ortho-para direction of that methyl group to help us put one of those two other groups on. Okay, so we can either put the amine on by adding a nitro group, or we can put the acyl group on by putting a nitro group on, by doing the Friedel-Crafts alkylation. Now we know that if we had that free amine, we can't do the Friedel-Crafts acylation. Okay, but if we did the nitration first, it would nitrate here or here, but the para would be the predominant product. Okay, so that means we can't nitrate now because we want the nitro group on these ortho positions. So we need to block that para position. So I think the next reaction we need to do is we need to put that carbonyl compound on there by doing a Friedel-Crafts acylation. Okay, so I'm going to do the next step in blue. So what we're going to do here to get that Friedel-Crafts acylation to go is we're going to have that, let's see, we have to have a methyl group on there, and then let's use an acid chloride. So we're using acetyl chloride plus aluminum chloride. Okay. Okay, we can use catalytic aluminum chloride up here or just one equivalent up there? Because the alkylation liberates our aluminum chloride back. But we have to use excess aluminum chloride when we do the acylation because that aluminum chloride will complex with that carbonyl compound. So make sure we use excess aluminum chloride, at least 2 equivalents, if not more. Okay, so when we do that, we're going to get 2 products, but our major product is going to be the para here because the group is coming in. So we're going to get a little bit of the ortho here, but we should be able to separate that. And it should still be, the para should be pretty close to our major product, okay? So now we've done that, and that's great, okay. So the next thing we can do is we can oxidize it with nitric acid, right? Do we have a problem with oxidizing with nitric acid? No, probably not, because the methyl group here, if we used some other oxidizing agent, like a chromic acid, that would oxidize off these benzylic hydrogens. With nitric acid, we're going to nitrate it. Now, let's look at this group here first. This group is a carbonyl compound, so it's a meta-director. So that means it's going to activate that position and that position. Okay. This methyl group is an ortho-para-director, but our para position's blocked. So it's also going to activate this position and this position. That means our next product from this reaction, if we use nitration, is going to give us our ketone compound.
Dr. Irvin, I'm
Yes.
sorry to interrupt. You've been freezing periodically while you're discussing these concepts.
Okay. Not sure how I can solve that. What part did we get to? I mean, the first reaction, the second reaction, the third reaction, or just all of it?
There was a part when you were discussing during the acylation where you froze. There was a part just recently that it's kind of hard to, like, go from like what you were saying to like where you end up when you're not freezing.
Okay.
Would you like us to like stop you when you're being frozen, or?
Yeah, please.
Yes, sir.
Let's see if are other people experiencing this as well?
Yes.
Yes. Okay, so it's my connection. All right. So, all right. I did see something pop up that's saying it was a little unstable. Let me switch. Okay, hang on. I'm going to switch internets and see if I can't stabilize this a bit. Okay, I've switched from my 5G to my 2.4. 5G, let's see if that was good. Okay, so let's go back a little bit to, okay, so on the first step, the Friedel-Crafts alkylation to give us that methyl group there, we got to that part and we said that, well, this is not our only product with the one methyl group because it's activating, we can isolate it from there. So this is going to be our next starting material here, okay? So now we had to figure out whether to do our nitration next or our Friedel-Crafts acylation next. And because our acyl group is para to our methyl group here, and our methyl group is ortho-para directing, okay, we are going to do that next, okay? Once we get this Friedel-Crafts acylation to go, and remember we have to use excess aluminum chloride here because once you form it, the aluminum chloride complex with the carbonyl compound. So we have to use excess aluminum chloride where we only have to use a smaller amount, catalytic or 1 mole amount in this one, okay? All right. So now we're down to the compound with the acyl group on the toluene right here. Now if we look at the directing of this acyl group, this carbonyl makes it a meta director, okay? So this carbonyl is directing into these meta positions here and here that are meta to this carbonyl compound. And the methyl group is a para director, but our para position is already blocked. So our methyl group is also directing to these meta positions here. So that means we can nitrate at this point because it's only going to nitrate at that one position, okay? So is it more stable now?
Yes, sir, quite. Thank you.
Okay, I need to make sure I go for that internet connection next time. Okay, so now that we have this, we have our methyl group, which is unaffected by the reduction, and our carbonyl group, which is also unaffected by the reduction. If we use a reducing agent like, if we use that reducing agent, it was just zinc and HCl, or tin and HCl. We don't want to use something like a hydrogenating agent or a lithium aluminum hydride because it'll attack the carbonyl. This zinc metal and HCl is very specific about only reducing down our nitro group to give us our meta amino toluene derivative here. Okay. So, all right, now that we have it, let's try to name this. Okay, we have an amino group and a methyl group on there. So that changes the name. What name do we get from that? When we have an amino and a methyl group on there, we have the toluidine group. And so we'll start 1, 2, 3, 4. So we have that 4 substituted toluidine group. Okay, so let me try this again with a more stable connection with a different compound. And what we're looking for in each step is, what do we use first because of activation and direction and possible interference with other groups? That's what we're looking for here, okay? So we're gonna, let me go ahead and erase this because I have, let me actually take a screenshot of it. There we go, good. All right, done. So I can make sure we put that on our, okay, go away, there we go. All right, I'm gonna erase all this now and we're gonna start. What functional groups do we want to have on this one? What's your favorite functional group? Don't say ethanol. Anybody have a favorite functional group there? No, okay. So let me do one. And let's see what we want to do. We want to do something that's interesting. So we're going to start with a benzene ring, of course. And let's do, ooh, I got a good one. That's a 2, NH2 up here. Okay, so this particular compound is used to make a modern plastic, a nylon type plastic. So it's really used industrially quite a bit, okay? So, but we have to back it down and we have to start with benzene again, okay? So let's see if we have that nitro group there. So this had to be in a nitro group at some point in time, so we need to nitrate. We have carboxylic acids here, and so we probably had to oxidize down using one of our reagents with an alkyl group. okay, because we can oxidize any alkyl group as long as it has a benzylic hydrogen down to a carboxylic acid. And the carboxylic acids are deactivators, so we probably don't want to have that on there ahead of time. So let's see what we got to do here. Again, we have to go where we have to start breaking things apart. Now we have these in in the ortho configuration. Ooh, we have a trick for that, don't we? If we use that sulfonic acid group, we can make that position so it doesn't use the para, it only uses the meta. Okay, so what I think we want to do is we want to start with benzene and add a methyl group to it. So if we start with benzene, okay, and we add a methyl group to it using methyl chloride and aluminum chloride right here, and we get our first derivative here, CH3 right here. Okay, now we could oxidize this immediately and turn it into a carboxylic acid, but then we'd have a meta director, okay? So maybe we don't want to oxidize it just yet, okay? But if we were to alkylate it again, we're going to get a significant amount of alkylation at that para position, okay? So what if we blocked that para position by using the sulfonic acid route, okay? So if we reacted it with sulfuric acid, H2SO4, we would get predominantly reaction at that site to do H2,3H plus a methyl group. Okay, so now we have that sulfonic acid here, and so we could do a Friedel-Crafts alkylation or acylation on this, right? Doesn't a sulfonic acid group make the Friedel-Crafts reaction not workable? Trying to find the page in the book there. So isn't one of the restrictions on that Friedel-Crafts reactions we can't have certain functional groups? Is this one of the functional groups we can't use on a Friedel-Crafts reaction because it's too deactivating? Okay. So, it says my internet connection is unstable. Am I chopping out again?
Your video is frozen, but so far you're good.
Okay, so red stripe on the screen now?
Yes, sir.
All right, good. Okay, so so we probably can't block it there using this kind of situation because we can't do the Friedel-Crafts alkylation using that sulfonic acid group in this way. So what do we want to do here? Okay, well, let's not do the sulfonic acid group yet. Let's just do another Friedel-Crafts on here, okay? Because the methyl group there activates it. So we're going to get two products from a Friedel-Crafts there. We're going to get the desired product, which is this meta product here, and we'll get the para product as well. Okay. So once we have this ortho product, we'll have to separate these and use just the one isomer here. Now, if we nitrate this, where is it going to nitrate? Okay. They are both ortho-para directors. Okay. So let's see where each of them is going to direct and see if we can get one isomer versus another. Okay, so what I'm going to do is I'm going to redraw this methyl group with blue ink and have the other methyl group as red ink, and we're going to see where each of the groups is directing and see if we have a preferential location for our nitration. Okay, so this is going to be activating this site here and this site here and this site here. Okay, which means that the other methyl group here is going to direct at this site here, And those are the only two sites. Okay.
Could
So
you,
then, go ahead.
so could you explain why the blue methyl directs towards that position? I thought that would be like meta to the blue.
Okay. So this is one, oh, yeah. Okay. Yeah, it doesn't do there, does it? Haha, you're right. I'm sorry. I jumped over that atom. Okay. So, all right. So that blue directs to this position and this position because those are para. This one directs to this position and this position because it's ortho, right? This is ortho to the green and this is para to the green, right?
Yes, sir.
Okay. So what it means is that each of these sites is equally activated, but these two sites are slightly more sterically hindered. So if we nitrate, it's going to nitrate at one of those two positions. And because of symmetry, those are equal positions and they are going to be meta to at least one of those groups. So what we want to do is, now that we have this, when we nitrate this, and we do, we end up with the isomer of CH3, CH3, NO2. Okay, because it's equally directed to this position and this position, because these positions here are sterically a little bit crowded because of the methyl groups. Okay, so this will be our primary isomer because of direction and sterics. Okay, so now we want to reduce down our amine or oxidize down our methyl groups. Okay, amines are really susceptible to oxidation, so I think we need to reduce or oxidize down our methyl groups to our carboxylic acids before we reduce down our amine. And how would we do that? What reagent do we have available to us to do that? Something like potassium permanganate. Potassium permanganate will give us our dicarboxylic acid product plus our nitro compound will be unaffected. Now the second step of this reaction here, we actually have to add acid to make sure we get protons back on here because permanganate's done in base, so we have to add acid at the last step here. Okay, so now we have our carboxylic acids there. We have our nitro group in the right place. So all we have to do is use that acidified reaction and add zinc and acid. HCl, not HCl2, right here. And the zinc, we're not using like a lithium aluminum hydride or a reagent like that. So it's not going to attack the carboxylic acids. It's only going to reduce down the nitrogen to the amine. Okay. So this is where knowing the selectivity of your reagent is very important. Because remember, in a couple chapters ago, we learned that lithium aluminum hydride will take carboxylic acids all the way down to primary alcohols, but it'll also reduce nitros down as well. So we had to be very selective about how to reduce down the nitro. Okay. So this is much longer stepwise than I would ask you to do on your exercise tomorrow, but the concept is the same. Which one do we choose first based on backing up and saying, well, this one would direct para, this one would direct meta, this one would direct ortho, by looking at it and backing up to figure out which direction you need to go. Okay, any questions on that? Okay, don't worry, we're gonna do this as part of our exercise tomorrow. I'm gonna go over this again, and I'm gonna have a few slides on a couple of reactions of benzynes and reductions of benzene rings as well. And we'll do those two sets tomorrow for our, before our exam on Friday.
Dr. Irvin, I actually had a question.
Yes.
So for the second methyl group, you just added 2 equivalents of the methyl chloride, is that correct?
We could have just added 2 equivalents of methyl chloride in the first reaction and got that as one of our isomers, yes.
Okay, and then you just isolate those two.
One's going to be the one is going to be the orthoxylene or the 1,2-dimethylbenzene, and one is going to be the paraxylene or the 1,4-methyl. And so
you would separate that through the polarity, and that's correct?
Yeah, they have different boiling points too. So we would separate those.
Okay, perfect.
Then only react the next one.
I had
Only react the ortho version.
I had a fast question as well, just procedural. The last 2 steps when we're talking about reducing the carboxylic acids and the nitrogen as well, would those have to be performed under very high heat since carboxylic acid is a deactivating agent?
No, because the reduction is happening at the nitrogen. And so this is a dissolving metal reaction where the zinc is actually going from zinc 0 to zinc +2. And so the reduction is actually happening at the nitrogen off the chain. So the carboxylic acids are unaffected by this reaction.
Okay, so the deactivating and activating, those effects only happen on the benzene ring, not to the outside substituents.
It's only the benzene substitution reactions.
Gotcha. Thank you very much.
That's actually a very important clarity on that particular thing. The activators are only on the actual substitution reactions on benzene, not the reactions around. Notice in the oxidation, we're actually doing a benzylic oxidation. So we're oxidizing off the ring, okay? And when we're doing that reduction of the nitro group, we're doing it off the ring. We're not reducing the benzene ring at all. Okay? So yeah, thank you for that clarity. That was important. Okay, so get your head around orthopara direction, activation, deactivation, and then trying to pick and choose our which path we need to choose. And that's what we'll work on a little bit tomorrow. We'll try to get those orthopara directors down and the activator, deactivator down before then, and that'll make the exercise tomorrow a little bit easier.
Will we have time for
what? Will we have time for what?
review?
Yes.
For the exam.
Yeah, so I only have about 3 or 4 slides for a couple reactions on benzene, and then I'll review the mechanism, orthopara direction, and deactivation. And then after, that'll take us up to about 1 o'clock, and then we'll have the activity after that. Okay? Okay. Mute. Oh, you're muted again, sorry. Okay. Okay, so yeah, we will have only about 10 or 15 minutes is going to be new material tomorrow, and then everything else is going to be review or the activity. So, all right, well, that brings us right here at 1:40. I'm going to stop recording. I'm going to try to stop recording. There we are. And